Hello everyone, welcome to the demonstration of GNAT Compiler. Firstly, what is a compiler? Compiler is a program that converts instructions into a machine code or lower level form so that they can be read and executed by a computer. Let us look into the details of a compiler by taking an example of GNAT Compiler. GNAT is an acronym for GNU ADA Translator. It is one such compiler and a front-end system for ADA 95 that uses the GCC backend as a retargetable code generator and is distributed according to the guidelines of the Free Software Foundation. The emergence of GNAT compiler dates back to 1992 at the New York University. It was developed by the combined effects of the NYU, ADA Core and the GNU project after being contracted by the US Air Force. Coming to the language support, the GNAT compiler supports all versions of the ADA programming language, and the higher versions like GNAT Pro and GNAT 3.15p support C and C++ languages also. Next up is the compiler architecture. The GNAT compiler is composed of two main parts, the front-end and the back-end. The front-end is written in ADA 95 and the back-end is the GCC backend extended to meet the needs of ADA semantics. The front-end comprises of 5 phases listed as lexical analysis, also known as scanning, the syntax analysis, also known as parsing, the semantic analysis, expansion, and the GG phase, which finally transforms the AST into an equivalent C tree. Now let us look into each of the front-end phase in brief. First is the lexical scanner, which analyzes the input characters and generates the associated tokens. The parser verifies the syntax of the tokens and creates the abstract syntax tree, abbreviated as the AST. The second phase is the semantic analyzer, which performs all static legality checks on the program and decorates the AST with semantic attributes. Next is a unique expander phase, which transforms high-level AST nodes into equivalent AST fragments built with lower-level abstraction nodes and, if required, calls to the ADA runtime library routines. Given that the code generation requires that such fragments carry all semantic attributes, every expansion activity must be followed by additional semantic processing on the generated tree. It can be seen as a backward arrow from the expander to the semantic analyzer. At the end of this process, the GG phase transforms the AST into a tree, which is read by the GCC backend. This phase is really an interface between the GNAT frontend and the GCC backend. In order to bridge the semantic gap between ADA and C, several GCC code generation routines have been extended and others added, so that the burden of translation is also assumed by GG and the GCC whenever it is awkward for or inefficient to perform the expansion in the frontend. All the above frontend phases communicate by means of a compact abstract syntax tree. The implementation details of the AST are hidden by several procedural interfaces that provide access to syntactic and semantic attributes. It is worth mentioning here that, strictly speaking, GNAT does not use a symbol table. Rather, all semantic information concerning program entities is stored in defining occurrences of these entities directly in the AST. The backend of a GNAT compiler is a unique GCC backend. The GCC backend generates assembly code for target machine. It is also worth mentioning here that the GCC backend is completely language independent and much of its code is machine independent as well. Other components of the compilation tool include a runtime management, which handles input-output, numeric libraries, etc. Also, many times a program is assembled from compilation of multiple files. It needs tools to ensure coherence, gather object files, record dependencies between units. This is handled by the library management essentials. Two such examples of library management essentials are GNAT bind and GNAT link. The strengths of the GNAT compiler is its ability to generate many useful warnings. The compilation speed is high on a multi-CPU machine. Also, the GNAT compiler is very much appreciated for its simplicity and many plugins are available in order to integrate with other tools. Also, the very few weaknesses of the GNAT compiler include its inability to support for exception handling and a poor GDB debugger. Now let us look into what all hardware devices are targeted by the GNAT compiler. The native platforms on which the GNAT compiler runs include GNU or Linux operating system on x86 64-bit machine, the Microsoft Windows operating system on i386 machine, and Mac OS on Darwin and x86 64-bit machines. The earlier versions of GNAT compiler come with a support to Solaris on SPARC, GNU or Linux operating system on i386, the Microsoft .NET operating system on i386. Also, the later versions like GNAT Pro Assurance supports operation on embedded systems. Last but not the least, I thank you all for your time, as here ends a demonstration on the GNAT compiler.